The mic is on? Okay, good. Okay, so today's two lectures will involve the study of Chebyshev polynomials. If you think about orthogonal polynomials as the monic polynomials that minimize L2 norms, Chebyshev polynomials are quite natural because they minimize L infinity norms. And L infinity, particularly if you're dealing with continuous functions, is almost more natural than L2. Same references, although there's a little bit about Chebyshev polynomials in this book. Anyhow, I remind you, we start out with a compact subset E of the complex plane, and the analog of the measure being non-trivial is that the set should have an infinite number of points. For any function, continuous function, but any function f, we define this as the sup norm, the L infinity norm on that set. The Chebyshev polynomial is a degree n monic polynomial that minimizes this L infinity norm. The minimizer is unique. We will prove that shortly in the case when E is an R. If I have a few minutes before the break, I can explain what you do when E is in C, but it's also not much harder. So it's appropriate to speak of the Chebyshev polynomial rather than a Chebyshev polynomial. Chebyshev invented his famous polynomials. The Chebyshev polynomials of the first kind are normally in the books defined by this relation, and certainly in his initial papers, Chebyshev doesn't have this relation at all. He did not define Chebyshev polynomials by this relation, but rather he asked the following question. What's the best degree n minus 1 polynomial that approximates x to the n on minus 1, 1? That is, that minimizes the norm of x to the n minus this polynomial. And if you think about it for a second, that's the same as asking for what the Chebyshev polynomial is. You just take you drop the monic piece and put a minus sign in front, and that's the best polynomial approximation. And he was interested in this polynomial approximation problem and solved it for minus 1, 1, and really it obeys this property, but he didn't. There's a very interesting quote that Soden and Uditsky unearthed. It's from a 1926 report that Lebesgue wrote on the work of Bernstein, because I think he was being considered for a position in France. I assume Lebesgue wrote it in French. I believe that their paper was originally in Russian, and it's translated into Russian, but there's an English translation of their paper, and so this is, right, French to Russian to English. But I think it's an accurate translation. It's not that it came out as hash. I assume that I am not the only one who does not understand the interest in and significance of these strange problems on maximum minima studied by Chebyshev in memoirs whose titles often begin with "on functions deviating least from 0, which is what this is. Deviating from 0 means minimizing L infinity norm. Could it be one must have a Slavic soul to understand the great Russian scholar? This quote is particularly bizarre because over 20 years before, Borel made important contributions to this subject, actually has a whole book more or less on the subject, and he was Lebesgue's thesis advisor. and did not have a Slavic soul, so far as I know. But anyhow, I think this quote is worth repeating. So we're going to focus on this talk almost entirely on the case where E is an R. The advantage of that, as we'll see, is Chebyshev polynomials in that case are just discriminants. That's the shocker. In that case, of course, Tn is real, since on the real line, if by real of Tn I mean the thing I take by taking the real parts of all the polynomials, this is smaller than absolute Tn, so if I want to minimize the absolute value, I may as well take the real part, because that doesn't change monic polynomials. We say that a polynomial Pn has an alternating set inside some compact subset E and R if there exist n plus 1 points, so n is the degree of the polynomial, remember, so that at the top point, when j equals n, the polynomial takes its maximum value on the set, and then on alternate points it takes maximum absolute value but flip sign. So it's got these n sign flips. And the basic idea of the following theorem is actually in the way Chebyshev constructed his Chebyshev polynomial, but the result, as formally stated, is due to Borel and Markov independently about 1905, although Markov's result was unpublished until someone published lecture notes long after he was dead in about the late 1940s. So, and the theorem is the following. It's called the alternation theorem. The Chebyshev polynomial of degree n has an alternating set. Conversely, any monic polynomial with an alternating set is the Chebyshev polynomial. So Chebyshev polynomials are entirely characterized by this property of having an alternating set. Here's the proof. Proof is not going to be very hard. Let Tn be the Chebyshev polynomial and look at all those points where it takes its maximum value and order them, label them so that they're linearly ordered. And you look at whether there's a sign change between successive maxima of absolute T. Suppose there are fewer than n sign changes in this set of points. Then we can find a degree n minus 1 polynomial or less that's non-vanishing at each yj and has the same sign as the Tn's, because we just look at the take your favorite point between strictly between a yj and a yj plus 1 where things change sign, and just arrange for q to change sign exactly at those points, to have zeros exactly at those points. If we now take epsilon small, it's fairly easy to convince yourself that Tn minus epsilon q will be a monic polynomial because it's degree n minus 1, and it has a smaller norm because I've pushed down the values at the points where it takes its maximum norm. And so if there have to be at least n sign flips, otherwise you didn't have the Chebyshev in the first place. So therefore there's an alternating set. On the other hand, let Pn be a monic polynomial with an alternating set, and let's suppose that the Chebyshev polynomial has a strictly smaller norm. And let's look at Pn minus Tn, Q, which I'll call Q. Q has the same sign as Pn at each of the points where Pn takes its maximum value, because this has a smaller absolute value there. So Q has to have at least n zeros because it also has alternating signs, but its degree at most n minus 1. So it can't have n zeros because if it changes sign n times, n plus 1 times, n times, it's got to have at least n zeros. So that, therefore, we have a contradiction, and we've proven this theorem. This immediately implies uniqueness. If Tn and Sn are two minimizers, so is their average. It's also a monic polynomial, and its norm is not any bigger. At the alternating points, we've got to have that Tn equals Sn because this has the same absolute value. It's a minimizer at those points. Sorry. I look at an alternating point of Q. This has the maximum value. That maximum value is equal to the maximum of Tn and Sn. The only way an average of two numbers which are between minus Tn and plus Tn can have an average which has absolute value equal Tn is if the two numbers are equal. So we know Tn equals Sn. There are n plus 1 points where this happens because that's the number of points in the alternating set, but the difference of the two polynomials is degree n minus 1. So the polynomial had better be identically 0 because any non-zero polynomial of degree at most n minus 1 has at most n zeros. Now I want you to notice that this is a profligate proof, right? In fact, I only need n points, and in the general complex case, one only gets it for n points, but it's the same idea. So now let's take my polynomial Tn, which is the Chebyshev polynomial, and let's look at it, pick an alternating set. There may be several alternating sets, right? It could be that on the support, on the set En, Pn can have a full n points where it takes its maximum, n points where it takes its minimum. There have to be n flips, but it can certainly happen that it takes its maximum. If I label these points, it can take its maximum the way I said. And originally, there will have to be n sign changes, but it might happen that there are two together, and then which one I put in the alternating set is a question of choice. So there isn't a unique alternating set, but there is, by the previous theorem, an alternating set. Obviously, between any 2 points in the alternating set, T has to have a 0 in R, not necessarily in E, right? Because this is a real polynomial, so if it changes sign between 2 points, there's got to be a 0 in between. And so we conclude that since there are only n zeros to begin with, all the zeros of the Chebyshev polynomials of a subset associated to a subset in R lie in R. They're all simple. You can't have double zeros, and they have to lie in the convex hull of E because they're between points in the alternating set which are in E. By a gap of a set E in R, I mean a bounded connected subset of the complement. So my E's are not in general finite gap sets, but it's a general feature that, of course, any compact subset of R has as its complement a at most countable union of open sets. Just one second. A countable union of open sets, each of open intervals, which are disjoint. Yeah.
You probably mean a bounded connected component of the complement.
I mean a bounded connected component. Thank you. Yes, that's what I mean by it has to be a component. Thank you. If there are only finite many gaps and no component of the set is a single point, then I'll speak of a finite gap set. This is the same usage I made before. between any two zeros of Tn, there's a point in the alternating set, right? Because we saw that, right, there was one zero between every pair of points in the alternating set. That accounts for all the zeros. So between any two zeros, there's a point in the alternating set, which means between any two zeros, there is a point in E, which means that each gap has at most one zero of the Chebyshev polynomial. So in particular, in the finite gap case, if we take a set with 27 gaps and we take the Chebyshev polynomial of order 1,000,000, 27 of the zeros can be one each in each gap, and all the remaining zeros have to be inside E. Moreover, it's not hard to see that Tn takes its maximum value at the bottom point of the set and at the top point of the set. That's an easy exercise for the reader. So at the endpoints of this convex set, we have this. That's what I just said. And as a result, if I let En be the inverse image of the set of points where Tn takes values between its minimum and maximum on E, that's a subset of the convex hull, because above and below it's strictly monotone. So En is a subset of the convex hull of E. On the other hand, En contains E, because obviously at any point in E, I'm in this inverse image. So En is a bigger set than E, and I'll jump ahead and tell you the punchline we're heading towards. The set En is a period n set. That is, it is exactly the spectrum of a periodic Schrödinger operator and Jacobi operator, and the discriminant of the corresponding Jacobi operator is a multiple of the Chebyshev polynomial. So that's the punchline we're heading towards. Okay, so I'm going to step back for a second before I do that. That's this next topic. I want to first note a useful lower bound on the norm of Tn. So recall we proved the Bernstein-Walsh lemma that said for any compact subset in E, if Qn is any polynomial of degree n, then we have this relation. Do I need a monic polynomial for this? No. For any polynomial. I apply this to the Chebyshev polynomials after, if you will, taking logs and subtracting n log z, or dividing out by z to the n and taking z to infinity. Since Qn is a monic polynomial, when I divide by z to the n, this converges to 1. This is a constant. And remember that g of e minus log z is in fact converges to the Robin constant. So we get this inequality, which remembering that the exponential of the Robin constant is the capacity, the exponential of minus the Robin constant is the capacity, we get this relation. So these norms are bounded from below by the capacity to the nth power. We'll see in a moment this is actually optimal in the sense that there are sets where you have equality. On the other hand, for sets in R, we'll a while later prove there's a lower bound with an extra 2 here, and that's also optimal. So let's step back and look at 2 examples. The first is the unit circle. its Green's function for the unit circle is log, outside the disk at least, is log z. It's inside 0 and outside it's log z. That's harmonic. It has a log z behavior at infinity, and it vanishes on the unit circle. So this is clearly the Green's function. Therefore, the capacity, which is the constant term in front of the log, sorry, the term after, the order 1 term after log z, the Robin constant is 0, and therefore the capacity is 1. So the unit circle has capacity 1. The TNs are monic. That means they obey this relation. That's just computing the value of the degree n coefficient, which means that in order for this integral to be 1, this absolute value has to have a maximum that's at least 1. So the norm of the Chebyshev of any polynomial has to be bigger than or equal to 1. In particular, Chebyshev does, but obviously z to the n has norm exactly 1. So the Chebyshev polynomials in this case are z to the n. Their norms are exactly 1, and that's the capacity to the nth power. So this is a trivial example where you can compute everything explicitly and see that the Zago lower bound is saturated. If I take minus 1, 1, it's known, and it follows from results we'll see in a few minutes. The capacity of minus 1, 1 is a half. One way of relating that to what we've seen before is the free Jacobi matrix is regular in the sense of Stahl-Totic. That means the nth root of the product of the a's, which converges to 1, is the capacity of the spectrum. Spectrum's minus 2, 2, so the capacity of minus 2, 2 is 1, so the capacity by scaling of minus 1, 1 is a half. By the alternating theorem, the Chebyshev polynomials of the first kind are multiples of Chebyshev polynomials, right? The polynomial that's defined by this relation, right, cosine n theta exactly has the right number of alternations in it. It's clearly an alternating polynomial. That's why Chebyshev wrote them down as, right, as theta runs from 0 to 2 pi, cosine theta runs from minus 1 to 1, and cosine n theta has alternating, it has n maxima, and well, n plus, whatever, you work it out, but it has the right number of, it has n zeros, and exactly there's an alternation between them. So they are multiples of the Chebyshev polynomials, and therefore, since one can work out that the Chebyshev polynomials of the first kind are not monic, because, right, cosine theta starts out, it's e to the I theta plus e to the minus I theta over 2, and the left-hand side is 1/2 e to the I theta, e to the I n theta plus e to the minus I n theta. When you take nth powers and work everything out, you see to get a monic polynomial, you have to multiply by 2 to the minus n plus 1. And on the other hand, the maximum of q is obviously 1. So the maximum of t is therefore 2 to the minus n plus 2, which is the promised 2 times the capacity to the nth power. So this saturates the lower bound with an extra 2. Okay. So now I want to relate this all to periodic Jacobi matrices, relate this whole thing to the subject we've heard about infinitely often from 4 or 5 different lecturers, and probably is even in the name of the conference. So I want to take a two-sided Jacobi matrix, periodic. We define tridiagonal matrices as usual. As before, we're interested in solutions of this equation. We study the p-step transfer matrix. As before, I remind you, we put the extra a's in the bottom of the transfer matrix to get determinant 1. And we saw that this transfer matrix can be written in terms of the first and second kind polynomials by this relation, and the discriminant was the trace. It's a real polynomial of degree exactly p, and its leading coefficient is exactly a1 up to ap to the minus 1. Because, right, the leading coefficient exactly comes from this term, and that's true for any orthogonal polynomial. We proved that the spectrum of the corresponding doubly periodic in both directions, Jacobi matrix was given by a union of closed intervals, and that this polynomial delta flipped sign between, over each band, there was a sign flip. The absolute value of delta, the maximum value of delta is 2. It has a, right, because on the spectrum of J, the maximum value of delta is 2. It has a sign change across each of the p bands. Therefore, the discriminant has a alternating set, which means if I take the discriminant and I multiply by the product of a's to get a monic polynomial, it's exactly the Chebyshev polynomial of degree n of this period n spectrum. So the alternating theorem guarantees us that the period J Jacobi matrix, if given its discriminant, this is the pth Chebyshev polynomial for the spectrum of J. It's certainly true that the 2pth Chebyshev polynomial is also a discriminant. It's a discriminant of this regarded as a period 2p. It is not in general true, in fact it's probably never true if any gap is open, that the other Chebyshev polynomials are discriminants of that set. For the spectrum of a periodic problem, this is only claimed its Chebyshev polynomials are explicitly given by discriminants only for multiples of p. Okay. Moreover, by this relation, this inverse image, the set I called En, is in fact the same as E. So for this case, En has that form. The idea of using somehow the discriminant or something a little like it, using polynomial inverse images, goes back to Geronimo and Van Asche, and there's a long series of papers by CALTECH on this subject. They, however, did not, I think, sufficiently exploit everything we know about periodic Jacobi matrices. And in some sense, in the work I'm going to talk about in the second lecture this afternoon, which is due to Christensen, Zinchenko, and myself, the main trick is to just exploit this periodic connection. Okay, I want to remind you that we also discussed the relation of potential theory in the discriminant. Given any periodic Jacobi matrix, the Green's function was given by this relation, where we take the branch of the square root with a positive z to the p. And we note that delta z over 2 is the same as TP over TPE, right? Because this is that multiple of delta which has maximum 1, and this also is that multiple of delta that has maximum 1. And reading off the regularity, the highest order term, one sees the capacity in this case is exactly the product of the pth roots. The measure's regular. Delta over 2 has this form. If you work out what that means, looking at the leading terms, this is monic, so the coefficient of the leading coefficient of this is t is 2 over t to the p. When you work everything out, given this relation, you see that the norm of Tp is exactly twice the capacity. Again, it saturates the lower bound. The conjugate to the log of q is the argument of q. It's given by q is the function that appeared inside the log there. It's given by arc cosine delta over 2, as we saw, and we concluded from this before that each band has harmonic measure 1 over p. Now, we also saw this had a converse. If all the harmonic measures are multiples of 1 over p, then we, as I explained in my lecture on the isospectral torus, there were Jacobi matrices of period p for which that was the spectrum. So a subset of E is a spectrum of a period p Jacobi matrix if and only if no more than p connected components and each component has harmonic measure k over p. Let's call a set E tilde, which is the spectrum of a period n. I've shifted now from p to n Jacobi matrix, a period n set. Now let's return to the general compact set E. Let this be an alternating set for Tn. Let's introduce change of notation, use the symbol Q for this maximum. At x0 and x2, Tn has value minus 2. I'm going to suppose n is even, so that means it's positive, negative, and that one's positive. Remember, this one's always positive, and then they alternate signs. So somewhere between these two, namely at x1, and we know that somewhere it has the value q. Now, if you have a function, continuous function takes the value minus q, somewhere in between it takes the value q. There are two possibilities. That point is the maximum in between, and then it's a double zero. Or there's a second point where it takes the value q. There could be 27 points where it, but there has to be at least a second. It follows that you've actually accounted for all the zeros at which Tn takes its maximum value, because between x0 and x2 there is either a double zero or two zeros. Between x2 and x4 there's either a double zero or two zeros. When you work out the arithmetic, you'll see you've accounted, right, between each of the even elements in the set you have 2 points. You've actually accounted for n points where it takes the value q, so you've accounted for all of them. So the set En is a set of intervals, perhaps glued together if there's a double zero. And if I look at 2Tn over q, I can write the Green's function explicitly for the set E. Same formula that I wrote for the set is a Green's function. It takes the value 0, it's harmonic outside En, and because the absolute value of the thing inside is 1, it vanishes, and I have the log, it vanishes on the set. So in fact, what we've proven, and therefore each of these intervals has harmonic measure 1 over p. So what we've proven is that E is a subset of En. En is in the set E, and En is a period n set with the same Chebyshev polynomial as E. And the norm of Tn is given by twice the capacity of this bigger set. Since E is contained in En, the capacity of En is bigger than the capacity of E, so this quantity is bigger than this quantity, so we've proven this lower bound with the extra factor of 2. This is a theorem first proven by Scheffermeyer about a dozen years ago, and it's an immediate consequence of this way of thinking of things. And his proof isn't so different, but the period p is a little bit obscure in what he did. But it really is a very beautiful result. Now let's suppose we take another set, which is a period n set. Let Sn be its nth Chebyshev polynomial. It's monic, so we must have that the norm of Sn is bigger than the norm of Tn over E. But if I now use the fact that the norm of this is twice the capacity of E tilde, we see the capacity of E tilde is bigger than the capacity of En. Taking into account the uniqueness of Tn, we see that among all period n sets that contain E, En is the one with minimal capacity. So one way of describing Chebyshev polynomials is you look at all period n sets that contain your set E, you look at that one that has minimal capacity, and its discriminant gives you the Chebyshev polynomial. Okay, the rest of the lecture that we have before the break is going to focus on some high points of the theory of Chebyshev polynomials from 1918 through 2010. And the first is a lovely theorem that I call the Faber-Fekete-Szego theorem. I'll say something about the history so you'll understand why it has that name. It was actually first written down by Szego, and it says the following: for any compact subset E in the complex plane, the nth root of the norm of the Chebyshev polynomials converges to C. This is somehow, if you will, an L infinity analog of regularity. We saw that the L2 norm, the nth root of the L2 norm of the orthogonal polynomials in the regular case converged to the capacity. That's exactly so this is exactly an analog of that. Given the Szego lower bound, we certainly get a lower bound on the lim-inf, because we have the Szego lower bounds that it was bigger than C of E to the n. When we take nth roots, we get numbers bigger than C of E. So it's not just, right, this is not just the limit, it's also the inf. One gets an upper bound by doing the following. So you take n plus 1 points and you form this interesting looking product of differences. We'll analyze that in a second. And by writing down polynomials where we in essence fix z1 up to zj, one sees that each of these products, if I soup over zn plus 1, I get a monic polynomial, which therefore has to have a norm which is bigger than that. If I now soup over the choices of the other points, you will see, I see that the soup of this quantity is an upper bound on the TNs. Fekete proved that, Fekete actually studied this object. He called it the transfinite diameter, and he proved that the transfinite diameter had a limit. Now, think about what this quantity is. You should think of z minus w not as z minus w, but as e to the log of the absolute value of z minus w. The log of this quantity is exactly a discrete Coulomb energy. This quantity is minimizing the Coulomb, the discrete Coulomb energy of n charges of weight 1 over n, where of course you ignore the self energies. So it's not quite the Coulomb energy as I've defined it before of the corresponding point measure, because that's infinite. But if I drop the self energies, you will not be surprised to learn that the self energies really don't, that in the limit, in fact, you can prove the minimizer for the discrete problem converges to a minimizer for the continuum problem, and the corresponding Coulomb energies with the self energies dropped converge. So I get e to a Robin constant, which is exactly the capacity to the n, and that's how Zago proved that, that's how Zago proved this fact. Okay. Now, Faber's name is associated to this theorem because of a 1919 paper in which he proved a result that's much more restrictive but also much stronger. It's more restrictive in that he only studied the special case where E is the interior of a single closed analytic Jordan region, or E is a Jordan, it's the same thing. He basically said, let's take an analytic Jordan curve and let's look at the exterior problem for that. And he really looked at, he looked at the Chebyshev polynomials for that problem. Now, he wasn't actually looking at Chebyshev. He didn't know he was looking at Chebyshev polynomials. But he was. He didn't think of it in those terms. Well, he actually did think of Chebyshev. Take it back. He actually proved more than just that the nth roots converged. He actually proved this ratio converges to 1, and he was actually able to get asymptotics of the Chebyshev polynomials. G of E is single-valued harmonic, so there's a function B of E which is bigger than 1 and therefore different from my Blaschke products, whose absolute value is the x of E, and the capacity, we have that B of E then behaves like Z over the capacity, and by using the fact that you had an analytic continuation, he was able to prove that uniformly on the exterior, including a neighborhood of E, so including all of E and a little bit inside, you had this very strong asymptotics. So he actually got an analog of Zago asymptotics in this case. He didn't mention Green's functions or capacities at all, though, because from his point of view, this function B of E was defined to be the conformal map of the exterior region into the exterior of the unit disk, and what I call the capacity was just the leading coefficient of this map at infinity. And some people knew this was the logarithmic capacity. I don't know if he did, but he didn't mention capacities or Green's functions at all in his paper. And the interesting thing is for Chebyshev polynomials, he had Zago asymptotics 2 years before Zago had Zago asymptotics for Chebyshev, for OPUC. So Faber was robbed. We should call it Faber asymptotics and not Zago asymptotics. Feketa's work was written in 23. He just proved this transfinite diameter existed, and its nth root, that was the nth root of these things, had a limit. And it was Zago who had a paper written, comments on a paper of Mr. M. Feketa. It was in German, so it was Herr M. Feketa. And he had the full theorem, and that I called the FFS theorem. Okay, next paper that I really want to mention. In '69, Whittam published a paper that was over 100 pages long that you can tell I like. I will describe it as a brilliant and seminal paper. It was on asymptotics of Chebyshev and orthogonal polynomials. And in his setup, E was always a finite union of either what he called analytic Jordan curves or Jordan arcs. So a Jordan arc, as I described last time, is a one-to-one image under an analytic map, a real analytic map of the closed interval 0, 1, and a Jordan curve is where it's not one-to-one at the endpoints. The two endpoints are the same. And it's analytic through the endpoint, the joined endpoint. In the case where E has these conditions and also is a subset of R, it's exactly a finite gap set. A finite gap set, right? An interval is an image, is a Jordan arc. So the finite gap sets are I should have said disjoint union, finite disjoint union of closed analytic Jordan curves or arcs. So, in the work of Faber, it's natural to look for an analytic function B with this property. The problem is, as we saw last time, there's the E that you have, you can analytically continue the B along any curve that avoids E, but there's no reason when you analytically continue along a closed curve that you get to where you started. The absolute value is the same because G is a harmonic function everywhere defined, but the phase is multi-valued. You therefore get these character automorphic functions, and the phase changes by this amount if I go around a loop, a subset G and E. So we have this problem that if this has a limit, the limit cannot be n independent because the characters of these analytic functions are n dependent. So we had this idea that I called the Whittam surmise. Namely, he had the idea of defining a function f of chi for each chi in the character group, continuous in chi. We call it in if we take the chi fn character associated with b of z to the minus n, and the limit is going to be these functions fn, which are now almost periodic in n. So therefore the polynomials are, and he had this idea for both orthogonal polynomials with respect to nice measures and for Chebyshev polynomials. And I'm not going to tell you what he got for orthogonal polynomials, but he found the right candidates for these f chi in the Chebyshev case. So remember, Chebyshev polynomials minimize some L infinity norm. And they minimize it with a condition about being monic near infinity. Now, we've divided out by b of z and c to the n, so in fact, the things that we are looking at, the approximate functions, the fact that the polynomials are monic, look like 1 at infinity. So he had the idea of looking at all character automorphic functions with the same character chi, which were infinity, at infinity took the value 1, and they minimized the L infinity norm, in this case, by a maximum principle, the value on the set you expect to be the same as the max everywhere. Of course, here you don't know you can take values on the set. You don't need that, though. It's the maximum. So this exactly captures the idea of Chebyshev polynomials minimizing an L infinity norm. The Chebyshev polynomials exactly solve this minimization problem, but where I demand that the a's be a polynomial times b of n, b to the minus n. He proved uniqueness of the minimizer for this, which was very important, by essentially finding an explicit formula in terms of theta functions. He also proved that this norm was continuous in chi. In fact, the solution was continuous in chi. And because of the uniqueness, the functions are continuous in chi, uniformly in Z, not, of course, on the whole covering space. And he proved the following theorems. First one is if E is a finite union of disjoint analytic curves, closed curves, Fn and Bn are as above, then in fact the norms behave the way you might expect, and the limit is exactly what I say it would be, namely this ratio should converge to the Fn's. And he proved this uniformly on compact sets. So he got what one could call Zago-Witten asymptotics for these Chebyshev polynomials. He also proved for a finite gap subset in R, in fact he proved for a union of closed arcs with no curves, I believe, is my memory. He proved the following. Notice this extra factor of 2 there. He certainly proved it for finite gap sets, and he proved it for certain other sets, and I don't remember what they were. I believe he proved it for any finite arc. No? Only the real line?
I will come in.
Okay. He conjectured, however, that his asymptotic result still holds. And he conjectured it looks like a strange conjecture because there seems to be a factor of 2 missing. And I should explain where the conjecture comes from. Because the norm is then twice as large as you might expect from the asymptotics. Of course, this is only uniform off the set, so we don't know what happens on the set. And he did this by looking at the case of -1, 1, where you can compute everything. The corresponding fn's are identically 1 because, right, it's the function 1. There are no characters anymore. So we want a function that's analytic outside the disk, outside -1, 1, that's analytic at infinity, takes the value 1 at infinity, and minimizes the L infinity norm, and the function 1 obviously does that. B in this case has this form. Its inverse, therefore, has this form. So B, which had magnitude 1, that was why we picked it. B of E was the x, the cosine of theta was exactly x, was exactly this. The Chebyshev polynomials were exactly 2 to the minus n times b to the n plus b to the minus n. We can now understand when z is in minus 1, 1, there are points where b to the n takes the value 1, in which case these add up, and I get 2 times 2 to the n. There are points where they cancel. So I have oscillation on the set, and the maximum norm has an extra 2. So that's why you get a 2, and that's what he was able to prove. On the other hand, off the set, this b is strictly bigger than 1. In this term, this doesn't matter anymore. This is negligible, and you lose a factor of 2. Both terms contribute on the set. Off the set, only one contributes. That's why he made his conjecture. To give you the punchline of the second talk, this conjecture, which was made in 1969, has now been proven by Christensen, Zinchenko, and me, and we'll see the proof. Whittam already did all the hard work. Okay. The other thing I want to say a couple of words about before we take the break is what I call the Totic approximation theorem and what I call Totic-Whittam upper bounds. So for any compact E, set E, Totic proved that there exist period n sets E so that the capacities converged. This was a useful fact because you can say a lot more for period n sets, and it was used as a tool in approximation theory. For the case of an arbitrary finite gap set, that there exist approximating sets with this property was proven independently by a number of other people, some of whom actually proved a stronger result, namely that if E is a L gap set, you can actually take a period n set with only L gaps. That's a harder result that isn't needed for the applications, but they actually have a slightly stronger theorem there. And the result was used by Totic and me, for example, to extend one of Lubinsky's proof of sinc kernel universality. In 2009, he published an improvement for the finite gap case. Namely, he was able to prove these capacities are in fact less than capacity of E times the error was of order 1 over n. Because of this relation, taking nth powers of capacities, you actually see that if E is a finite gap set, it follows from Totic's bounds that the norms are bounded by a power of the capacity of the n. Remember, we had a lower bound with a 2. Now, this was actually follows from Whittam's result, because in the finite gap case, this also was done by Whittam. But Totic's proof, I mean, you really need a large chunk of this 100-page paper to get this result in the finite gap case, and Totic's proof was much simpler. We'll have an even simpler proof in the next hour. And neither of the earlier proofs has very explicit bounds estimates for D. In general, even though they only had finite gap sets, if we have a general set A, we'll say it has, E will say it has Totic-Whittam bounds if there's an upper bound of that form. And we will prove, for example, that positive measure Cantor sets have Totic-Whittam bounds after the break. So this is what I want to say before the break. After the break, we will turn to these results that Christensen, Zinchenko, and I have proven.
Okay, thank you very much.
Yeah.
In the Totic approximation theorem, can one say anything about the nearness of the sets, with which you're approximating the capacity, like say the measure of the symmetric difference or the Hausdorff metric between the two sets?
So Hausdorff metric certainly not, because the ENs can have extra little points in general inside. Maybe you can fix that. That I don't know. It certainly, you can say it in many, many cases, say the difference is very small. It's not going to have small Hausdorff dimension because it's a finite gap set. So, but what can happen is you can have very tiny, exponentially small bands in some of the gaps. So the difference of the measures is probably exponentially small. I don't know if that's actually been proven in general. It's certainly, in the finite gap case, it has essentially been. No, I take it back, it's polynomial. I take it back, it's polynomial. Anyhow, there are some explicit estimates in some of the proofs.
Can I make a small comment?
Yep, absolutely.
So, let us consider such case.
Actually, you need the permission of the chairman.
Assume that we have such case. We have a circle and interval, symmetric. And when we try to find Chebyshev polynomial for this set, so if this is extremely small, almost zero, then it should behave like C of E power n. But if we close this, if this circle is very small, it should behave actually like 2 times C power n. And so for this case, I can write, with Totic, we are able to write explicitly what is the leading term in the second asymptotics. With respect to n, it will be an almost periodic function, which can be written explicitly. So one can find explicitly the second term in asymptotics for such system. And the second thing that...
So just to put it, so what you're saying is for this set, this certainly fails.
Yes.
With the 2.
And also, what is known, Chebyshev polynomial for a circle arc. And this is also interesting. Very nice example. As soon as you put it to a complete circle, it should give you constant 1. You can write it to the small piece. It would be exactly 2, like an interval. And also this extreme polynomial is known, and this number explicitly is known.
And is not 2.
It's field dependent of alpha, and it's changed from from 1 when you close to 2 when you open complete.
So I guess Whittem only had this, as I stated it, for finite gap sets.
We don't have the conjecture that as soon as you have such thing, it should be true, but it's wrong, and we theoretically wrote the paper.
So while we proved one of Whittem's conjectures a few years before, they disproved another one of Whittem's conjectures.
So can we continue?
There's a coffee break now, isn't there?
No, coffee break after.
No, coffee break is now, isn't it?
Okay, thank you. Sorry.